Message from the depths of space. From the unknown. The secret of K2-18b. 124 light-years away, a planet floating in the silence and depths of dark space, 8 times larger than Earth, is sending us the most important signal in history. This tells us we are not alone. The James Webb Space Telescope has discovered molecules in this world's atmosphere that are produced only by living things: dimethyl sulfide, methane patterns, and water traces. All of these perfectly overlap with the chemical fingerprints of life. This is no longer a prediction. Scientists are calculating that there is a 99.7% probability that biological processes are currently occurring on this distant ocean planet. If you liked and subscribed to discover this discovery that will change the course of history, we can start exploring together. Did the impossible become real? The single word that astronomer Niku Marushiden whispered in the face of the rainbow lines appearing on his computer screen: impossible. What was before his eyes was something that was expected and should not exist. The spectral data flowing from James Webb was coming from a planet 124 light-years away, from a world whose light set out before humans invented writing. But there, molecules shining in infrared wavelengths contained a message written in life's own unique language. We can think of it like this. It's like trying to detect a single drop of perfume in a swimming pool from 3 meters away. James Webb had accomplished exactly that. From 124 light-years of space, it had captured trace amounts of specific molecules in the atmosphere of planet K2-18b. Each light wave was telling a story about which gases were floating in that distant sky, and the story they told was breathtaking. The data revealed something called dimethyl sulfide floating in those distant clouds. On Earth, this molecule has one source: living organisms. Marine phytoplankton pump this molecule into our atmosphere every day. This is a sign of biological activity as distinctive as a fingerprint. But the surprise might not have been limited to this. There were other things hidden in the rainbow spectrum. Methane and carbon dioxide were appearing in ratios matching early Earth's atmospheric chemistry, when our planet was young and filled with primitive life. Water vapor signals were dancing in the data like liquid evidence of vast oceans beneath hydrogen clouds. Madhusan called his colleague at Cambridge University. "You need to see this immediately," he said, barely controlling the excitement of discovering something that changes everything. "We're looking at atmospheric chemistry for which we can find no natural explanation other than life." The numbers were astonishing. Probability calculations kept pointing to the same result. In this world, right now, at this very moment, biological processes were actively occurring. Even as you read these words, the atmosphere contained the exact gas mixture expected from a living ocean ecosystem. For decades, scientists had searched the cosmos for traces of life beyond Earth. They had found frozen water on Mars, organic compounds in asteroids, and potentially habitable worlds orbiting distant stars. But they had never found anything like this: active, ongoing biological signals flowing through space like a cosmic business card. The discovery could change the world. The Discovery team repeated the analysis in 17 different ways. Every mathematical model, every chemical simulation, every atmospheric physics calculation pointed to the same striking conclusion: something alive in the sky of planet K2-18b was breathing, eating, reproducing, and dying. What made this discovery even more extraordinary was that it almost never happened. James Webb had been directed at this planet not specifically to search for life, but to study its basic atmospheric composition. The biological signatures emerged as an unexpected bonus, a cosmic gift wrapped in starlight and delivered from the boundless void of space. However, this was only the beginning of a story that would rewrite every page of astrobiology textbooks. Within hours of the discovery announcement, every major observatory on Earth was trying to turn their instruments toward the constellation Leo. K2-18b had transformed from an obscure catalog entry into the most important celestial object in human history. Astronomers who had spent their careers studying distant galaxies were suddenly canceling their observations and focusing on this single point of light floating in the cosmic darkness. Intercontinental conference calls erupted. Science teams were coordinating the largest joint observation campaign ever attempted. So, what about the evidence? Chemical evidence. Dimethyl sulfide. Dimethyl sulfide smells like a mixture of rotten cabbage and ocean water, but it could be the most important molecule in the universe. This simple chemical compound consists of only 5 atoms, 2 carbon atoms surrounding sulfur, each bonded to 3 hydrogen atoms. On Earth, every single dimethyl sulfide molecule in our atmosphere comes from the same source, living organisms. There is no known geological process, chemical reaction, or natural phenomenon that can create this molecule without biology. Imagine the most remote oceans on our planet, thousands of miles from any land. Even there, microscopic phytoplankton constantly pump dimethyl sulfide into the atmosphere as they go about their daily business of photosynthesis and reproduction. These tiny marine organisms produce approximately 20 million tons of this chemical every year, making it the primary sulfur source in Earth's air. Scientists conducted extensive research to search for non-biological ways to produce dimethyl sulfide. They subjected various minerals to extreme temperatures and pressures. They simulated lightning strikes, volcanic eruptions, and asteroid impacts. They tested every kind of chemical reaction that could naturally occur on a rocky planet. The result was always the same: no dimethyl sulfide without life. The detection of this molecule in K2-18b's atmosphere created an earthquake effect in the scientific world, precisely because of this biological characteristic. When James Webb identified the spectral signature of dimethyl sulfide in those distant clouds, it was essentially detecting the waste products of alien metabolism floating in space. But the discovery becomes even more attention-grabbing here. The dimethyl sulfide concentration detected around K2-18b is actually higher than the levels we typically measure in Earth's atmosphere. This shows that the organisms producing it on that distant world are either more abundant or more active than the phytoplankton in our own oceans. The implications challenge the imagination. We're not just looking at evidence of life, we're looking at potentially thriving, abundant life, an entire ecosystem of microscopic organisms breathing, eating, reproducing, and releasing their chemical waste products into an alien sky 124 light-years away. Mathematical certainty, 99.7% probability. Mathematics doesn't lie, and the numbers flowing back from K2-18b were telling an incredible story. Scientists don't just look at atmospheric data and predict that life might exist. They use sophisticated mathematical models that calculate probabilities based on thousands of different variables. Think of it like a cosmic crime scene investigation, where each molecule is a piece of evidence that either supports or refutes the biological activity hypothesis. The calculation begins with something called the chemical disequilibrium principle. In a lifeless world, atmospheric chemistry tends toward an equilibrium state, where all possible chemical reactions have been completed. Oxygen reacts with methane until one or both are consumed. Carbon dioxide dissolves into any available water. Over millions of years, the atmosphere settles into a stable, predictable pattern. Life completely upsets this balance. Living organisms constantly pump gases into the atmosphere that shouldn't coexist under normal chemical conditions. They produce oxygen and methane simultaneously, even though they react with each other. K2-18b's atmosphere showed chemical signatures wildly out of equilibrium. Methane coexisted with water vapor in concentrations that defied purely geological explanations. Carbon dioxide levels were fluctuating in patterns suggesting active removal and replenishment. Researchers ran computer simulations and modeled every kind of non-biological process that could explain the observations. They tested scenarios involving volcanic activity, lightning strikes, meteor impacts, and exotic atmospheric chemistry. The results were definitive. The probability that purely geological processes could produce the observed atmospheric chemistry was less than 0.3%. This meant there was a 99.7% chance that biological activity was responsible for the chemical signatures. Probability calculations had crossed the threshold that scientists use to claim a discovery. The same statistical standard applies to everything, from particle physics to climate science. These weren't wild speculations or hopeful interpretations. They were cold, hard numbers produced by rigorous mathematical analysis of empirical observations. The universe had presented humanity with an equation, and the solution was life. Perfect world. Goldilocks zone. Sometimes the universe aligns in ways that are almost too perfect to be accidental. K2-18b represents one of these cosmic coincidences. This world sits in what astronomers call the Goldilocks zone, not too hot, not too cold, but just right for liquid water to exist on the surface. But location alone doesn't guarantee habitability. Hundreds of other exoplanets orbit within their stars' habitable zones, but most are hostile to life as we know it. What makes this particular world so extraordinary is the number of different factors combining to create potentially perfect conditions. The planet's mass is crucial to its success. Being 8.6 times heavier than Earth means it has enough gravitational pull to hold on to a thick atmosphere, while avoiding the crushing pressures that would make surface conditions unbearable. K2-18b's size also means it formed with abundant water. Planets in this mass range can capture and retain hydrogen atmospheres during their formation, creating conditions where water vapor can condense into vast global oceans. Computer models show that this world could be completely covered with water hundreds of miles deep, an ocean planet with no dry land anywhere. The star system provides another layer of perfection. K2-18b orbits a red dwarf star that burns cooler and longer than our Sun. Orbital characteristics create additional advantages. K2-18b completes one orbit around its star every 73 Earth days, which means its year is much shorter than ours. However, because its star is cooler, the planet receives almost exactly the same amount of energy as Earth receives from our Sun. All these factors combine to create what scientists call a potential super-habitable world, a planet that could actually be more suitable for life than Earth itself. Ocean signatures. Steam rising from a boiling kettle tells you there's water inside, and the universe has now shown us steam rising from an entire planet. The James Webb Space Telescope didn't just detect random water molecules floating in space around K2-18b. The instruments revealed specific water vapor patterns that could only come from exchange between vast liquid oceans and the atmosphere. Think of it like cosmic fingerprinting. The way water behaves when transitioning from liquid to gas creates unmistakable spectral signatures that astronomers can read like a book. Water vapor detection came through a process called transmission spectroscopy. When K2-18 passes in front of its star, starlight filters through the planet's atmosphere before reaching our telescopes. Water molecules in that atmosphere absorb specific wavelengths of infrared light, creating dark lines in the spectrum that reveal both water's presence and behavior. Concentration also provided clues about the scale of these alien seas. Computer models show that the atmosphere contains enough water vapor to indicate surface oceans covering the entire planet to depths potentially reaching hundreds of miles. We're not talking about scattered lakes or polar ice caps. We're looking at a true water world where the ocean is higher than the highest mountains. Perhaps most remarkably, the water vapor contained dissolved gases that further detailed the story. Spectral analysis revealed traces of sulfur compounds and organic molecules mixed with water vapor, exactly what you'd expect if the oceans were filled with microscopic life forms, processing nutrients and releasing waste products. Life traces in the atmosphere. The air hanging over K2-18b tells a story that scientists have seen only once before, in the ancient rocks of early Earth. Methane and carbon dioxide don't normally coexist in planetary atmospheres for very long. These two gases react with each other through photochemical processes triggered by starlight, rapidly converting into water vapor and other compounds. In a lifeless world, typically one gas dominates while the other disappears. The persistence of both gases in significant quantities around K2-18b suggests that something is actively producing them faster than chemistry can destroy them. The ratio between these gases is particularly striking. Spectral analysis revealed methane concentrations of approximately 100 parts per million, while carbon dioxide measured around 400 parts per million. This 2-to-1 ratio almost perfectly matches the atmospheric composition that scientists believe existed on Earth 3 billion years ago, at the height of our planet's microbial age. Think of these gases like exhaust from two different types of biological engines. Methane is typically produced by organisms called methanogens, microscopic life forms that thrive in oxygen-free environments and produce methane as a waste product of their metabolism. Carbon dioxide comes from a wide variety of biological processes, including respiration, decomposition, and photosynthesis. The simultaneous presence of both gases in such high concentrations can only be sustained by active biological production. Computer models show that geological processes alone cannot sustain these concentrations against the relentless photochemical destruction caused by stellar radiation. Smoking gun. Dimethyl sulfide again. In the cosmic courtroom where scientists weigh evidence for extraterrestrial life, dimethyl sulfide has just given the strongest testimony. This molecule represents what forensic scientists call a smoking gun, evidence so specific and unambiguous that it points to only one possible explanation. Unlike water vapor, which could have geological sources, or methane, which could come from rock chemistry, dimethyl sulfide has never been found in nature without biology. The detection came from James Webb's most sensitive infrared instrument, which identified the unique spectral fingerprint of dimethyl sulfide molecules floating in K2-18b's atmosphere. The signal was weak but unmistakable, like hearing a whisper in a crowded room but knowing exactly who spoke because you recognize their voice. What makes this discovery so revolutionary is the complete impossibility of creating dimethyl sulfide through non-biological processes. Perhaps most remarkably, the isotopic signature of the detected dimethyl sulfide matches patterns produced by biological processes rather than any conceivable geological source. The discovery team subjected their findings to modern astronomy's most rigorous peer review process. They invited skeptical colleagues to examine the data, reanalyze the spectral signatures, and search for alternative explanations. The conclusion didn't change. Biology was the only valid explanation. James Webb scalpel made of starlight. Looking at K2-18b with the James Webb Space Telescope is like performing surgery with a scalpel made of starlight at distances that challenge human comprehension. The telescope doesn't actually take pictures of distant planets the way you might imagine. K2-18b is too small and dim to appear as anything other than an invisible dot lost in its parent star's brightness. Instead, James Webb uses a technique called transit spectroscopy that transforms the entire planet into a cosmic laboratory where we can analyze alien atmospheres one molecule at a time. Every 73 days, K2-18 passes directly between its star and Earth, creating what astronomers call a transit event. During these cosmic eclipses, the planet blocks approximately 0.1% of its star's light. Think of it like holding a colored filter in front of your flashlight. The filter blocks certain colors while allowing others to pass through, creating a unique pattern that tells you about the filter's composition. K2-18b's atmosphere works exactly the same way. The technical achievement is astounding. James Webb is essentially analyzing individual molecules floating around a planet 124 light-years away. To put this in perspective, this is like being able to identify the specific type of perfume someone is wearing from a distance of 750 trillion miles. Red dwarf, cosmic hearth. K2-18 burns with the gentle warmth of a cosmic hearth, providing stable energy that has nurtured potential life for billions of years. This red dwarf star represents everything our sun is not: smaller, cooler, dimmer, and destined to burn for trillions of years instead of our sun's mere 10 billion year lifespan. At first glance, red dwarfs seem like terrible places to search for life. These stars are notorious for producing violent flares that can strip away planetary atmospheres and sterilize any life forms on nearby worlds. However, K2-18 appears remarkably well behaved for a red dwarf. The star's surface temperature is approximately 3,300 degrees Celsius, making it significantly cooler than our sun's 5,500 degrees Celsius surface. This means K2-18b must orbit much closer to its star to receive adequate energy for liquid water. The planet completes one orbit around its star every 73 Earth days, at approximately 23 million kilometers distance, about 6 times closer than Earth orbits the Sun. The star's age provides another important advantage for life development. K2-18 is estimated to be at least 5 billion years old, meaning it has been providing stable energy to its planetary system longer than life has existed on Earth. Air breathes. Seasonal changes. The air above K2-18b breathes with rhythms reflecting the pulse of living worlds. Scientists weren't expecting to find weather on this distant world, but spectral data revealed atmospheric compositions fluctuating over time periods matching the planet's 73-day orbital cycle. Seasonal variations provide important evidence for active surface processes rather than static atmospheric chemistry. A lifeless world with a stagnant atmosphere would show very little change over time. However, K2-18b's atmosphere appears to be constantly changing and evolving. As surface temperatures change, water vapor levels fluctuate, showing active evaporation and condensation cycles carrying moisture between ocean and atmosphere. Methane concentrations show particularly dramatic seasonal variations, suggesting biological rather than geological origins. Geological methane production typically remains stable over long time periods, but biological methane production can fluctuate rapidly in response to environmental changes like temperature, nutrient availability, and seasonal light cycles. Temperature paradise. Temperature readings from K2-18b tell a story of perfect cosmic timing, with surface temperatures navigating the narrow range where water transforms from ice to liquid to steam. Thermal infrared measurements reveal average surface temperatures between 4 and 27 degrees Celsius across most of the planet's surface, strikingly similar to the temperature range found in Earth's temperate oceans, where life is most abundant. This cosmic coincidence occurs despite the planet's very different atmospheric composition and stellar environment. Temperature stability comes from K2-18b's thick hydrogen atmosphere, acting like a planetary blanket that distributes heat evenly worldwide. Perhaps most importantly, temperature ranges appear to have remained stable for potentially billions of years. Stellar evolution models show that K2-18 has provided consistent energy output throughout its lifetime, allowing the planet to maintain habitable temperatures across geological timescales that dwarf human civilization. Magnetic shield. Invisible magnetic force lines wrap around K2-18b like cosmic armor, deflecting the deadly particles that have sterilized countless other worlds across the galaxy. Magnetic fields don't just point compasses in the right direction, they serve as planetary life support systems that determine whether worlds can protect their atmosphere and preserve surface life. K2-18's magnetic field strength appears comparable to Earth's, based on indirect measurements, relying on how the planet's atmosphere interacts with charged particles from its star. Magnetic protection allows the thick hydrogen atmosphere to persist rather than gradually eroding away over millions of years. The magnetic field originates from the planet's molten core, where electric currents produced by liquid metal motion create magnetic field lines extending into space around the world. Perhaps most remarkably, the strength and configuration of K2-18b's magnetic field appears nearly optimal for protecting life. Similarity to Earth. The molecular signatures flowing from K2-18b read like a chemical recipe written by Earth's own ocean microbes, replicated across 124 light years of space. When scientists compared this distant world's atmospheric chemistry to the known biological signatures of Earth's marine ecosystems, the similarities were so precise they seemed almost impossible. Sulfur compound ratios, carbon molecule isotopic patterns, and trace gas concentration gradients match the exact fingerprints left by phytoplankton blooms in our own oceans. Perhaps most striking was that the isotopic signatures told a story of biological fractionation, the process by which living organisms preferentially use certain isotopes of elements during metabolism. Missed opportunities. For decades, humanity's most powerful telescope looked directly at K2-18b and saw nothing but an ordinary exoplanet, missing humanity's greatest discovery by technological centimeters. The Hubble Space Telescope first detected K2-18b in 2015, measuring its size, orbit, and basic atmospheric properties. Hubble even identified water vapor in the planet's atmosphere, confirming this world had habitability potential. However, the biological signatures that would revolutionize our understanding of life in the universe remained completely invisible to Hubble's instruments. The problem wasn't a lack of observational skill or scientific insight. It was entirely a technological limitation. James Webb's revolutionary design finally bridged this technological chasm. While the telescope's massive mirror collects 25 times more light than Hubble, its specialized infrared instruments can detect molecular signatures with unprecedented precision. Hydrogen paradox. Everything astronomers thought they knew about hydrogen atmospheres was wrong, and K2-18b rewrote the textbook on planetary habitability. For decades, scientists assumed thick hydrogen atmospheres would be hostile to life as we know it. Hydrogen is highly reactive, potentially explosive, and completely different from the nitrogen-oxygen atmosphere that sustains life on Earth. K2-18b forced a complete reversal of this thinking. The planet's hydrogen atmosphere isn't just compatible with life, it actually provides important advantages that could make the world more habitable than Earth itself. The hydrogen atmosphere creates an incredibly efficient greenhouse effect that maintains stable temperatures across the entire planet. Unlike Earth's patchy climate with frozen poles and scorching deserts, K2-18b's hydrogen blanket distributes heat so evenly that surface temperatures remain within the liquid water range from equator to pole. Cloud dynamics. The sky above K2-18b swirls with cloud patterns, creating a planetary greenhouse perfectly tuned for biochemistry. Infrared imaging reveals cloud formations extending for thousands of miles, creating weather systems that efficiently distribute heat, moisture, and chemical nutrients across the entire planet. The clouds themselves primarily consist of water vapor and organic compounds, creating a chemical soup in the atmosphere that facilitates the complex reactions needed for biological processes. Think of these clouds as floating laboratories, where atmospheric chemistry creates the building blocks of life before raining them down onto the planet's global ocean. 8 billion years of evolution. K2-18b has potentially been sitting in the cosmic sweet spot for 8 billion years, giving life time not just to emerge, but to evolve into forms we can't even imagine. Stellar evolution models reveal that K2-18b has maintained habitable conditions for a timespan that dwarfs Earth's entire biological history. While life on our planet has existed for approximately 3.8 billion years, this distant world was potentially suitable for biological activity before our solar system formed. The 8 billion year potential habitability timespan puts K2-18b's biological evolution roughly twice as far along as Earth's. If life emerged on this world at the rate it appeared on our planet, alien organisms could have been evolving for billions of years longer than terrestrial biology. Alien microbial life. Alien microbes floating in the dark depths of K2-18b's global ocean are probably living lives reflecting Earth's most ancient organisms, but with 8 billion years of evolution to perfect their survival strategies. The chemical signatures flowing from this distant world paint a picture of marine ecosystems dominated by extremophile organisms, microscopic lifeforms thriving in boiling hot springs, crushing ocean depths, and toxic chemical environments. In the depths of K2-18b's global ocean, volcanic vents are probably pumping the chemical components of life into alien seas, creating underwater gardens where evolution flourishes in the planet's hidden depths. The planet's large size and active geology suggest extensive volcanic activity, providing much more diverse chemistry than would be possible in a geologically dead world. Webb's technological triumph. The James Webb Space Telescope represents the culmination of 30 years of technological development, creating capabilities that transform impossible observations into routine measurements across cosmic distances. The telescope's primary mirror spans 6.5 meters in diameter when fully deployed, making it the largest mirror launched into space. However, size alone doesn't explain Webb's revolutionary capabilities. Perhaps most remarkably, Webb's design incorporates sufficient redundancy and upgradability to continue making discoveries for at least 20 years. Interplanetary exploration. A spacecraft the size of a washing machine could reach K218b within 40 years using propulsion technology that already exists, carrying instruments capable of definitively confirming whether alien life is thriving in those distant oceans. The journey would require launching the probe using conventional chemical rockets to escape Earth's gravity, then deploying advanced ion propulsion systems that could accelerate the spacecraft to approximately 20% the speed of light over several decades. K218b has siblings scattered across the galaxy, and the James Webb Space Telescope is systematically hunting them down to determine whether life is a cosmic rarity or a universal phenomenon. The discovery of biological signatures on K218b triggered the largest coordinated exoplanet observation campaign in astronomy history. Drake equation being rewritten. The numbers that have haunted scientists for decades are suddenly rewriting themselves, transforming humanity from a cosmic accident into one member of a vast galactic community. The Drake equation, formulated in 1961, attempts to estimate the number of communicating civilizations in our galaxy by multiplying factors like star formation rates, planetary formation, and the probability of life developing. K218b has provided the first reliable measurement of an important Drake equation factor, the fraction of potentially habitable planets that actually harbor life. Meaning for humanity. The detection of life on K218b shattered humanity's cosmic isolation and forced our species to confront the deepest questions about existence, purpose, and our responsibilities as members of a living universe. Religious institutions around the world are grappling with theological implications that challenge fundamental assumptions about creation, divine purpose, and humanity's special relationship with the cosmos. Education systems are scrambling to update curricula that suddenly seem outdated and Earth-centric. Textbooks in every scientific discipline need revision to account for the new reality that life appears widespread rather than rare. New age of astrobiology. Every astrobiology textbook published before the detection of dimethyl sulfide on K218b has become a historical artifact, invalidated by observations that transform speculation into established scientific fact. The discovery represents the transition from theoretical to empirical astrobiology, the difference between wondering whether life exists elsewhere and actually studying alien biological processes through direct observation. For the first time in human history, astrobiologists have real data about extraterrestrial life rather than educated guesses based on terrestrial biology. The discovery validated decades of theoretical work while simultaneously revealing how much scientists didn't understand about biological processes in extraterrestrial environments. Final word: a new age. Textbooks were being rewritten in real time. Scientists were racing to understand the implications of a discovery that transformed speculation into reality and launched humanity into a new age of cosmic biology. K218b is not just a scientific curiosity, it represents the answer to one of humanity's oldest questions: are we alone? For the first time in human history, the data was pointing to a powerful no. And this is just the beginning. Don't forget to subscribe to explore more data together. Merry Christmas. Good night.